Hi class, welcome to lab exercise 12. This is on respiratory volumes. In Canvas, I mistakenly identified this as being lab 13. It is not, this is lab 12 with the week of beginning November 23rd. So you've got lab exercise 12 available to you. Please do take a look at the lecture video so that you understand how to go through the interpretation of spirometry of the pulmonary function tests, because I explained that material there. So I'm going to go through the 3 Physio Ex activities that are part of lab exercise 12. And then you've got a little bit more work in the lab exercise itself to complete. So, this is an experiment we would be doing on BioPack if we were meeting in the laboratory, but it's just too challenging to utilize BioPack. Too many students are having a hard time with that software, and I felt that that wasn't fair to continue to use something that was a pain for a significant portion of the class, including myself. I still have trouble operating BioPack on my computer, even though it's a new computer. So I'll demonstrate these 3 activities for you here. These are the Physio Ex activities, Physio Ex exercises 7, activities 1, 2, and 3. Okay, so here's the objectives for the first activity. And it begins by talking about what ventilation is, right? That includes the process of inspiration and expiration. We've learned about the different muscles that are involved in inspiration versus expiration. For example, inspiration uses the diaphragm. It contracts, as well as the external intercostal muscles, whereas expiration uses other muscles and does not utilize the diaphragm. So here are some of the many terms with respiratory sciences. So we've got our tidal volume, the different reserve volumes, our residual volume, total lung capacity, vital capacity, and then the forced vital capacity. So we have 4 volumes, and those are our defined volumes. But there are capacities, and capacities are the sum of 2 or more volumes. For example, the vital capacity is equal to the tidal volume plus the inspiratory reserve volume plus the expiratory reserve volume. All right, let's move forward. Okay, now the FEV1 measurement and the FVC measurements, these can be used to help the diagnostician understand if a person has obstructive airway disease versus restrictive airway disease. These are completely different categories of airway disease. But I would like to emphasize that it is possible for the same person to have both. For example, I have asthma, and that is an obstructive disease, but I also have some fibrosis in my lungs from lupus, an autoimmune disease. So that is restrictive. So I have both components. All right, but the general rule of thumb is that if we see an FEV1 divided by FVC that is 80% or below, that means restrictive disease. The thing about obstructive disease is, yes, these values change. The forced expiratory volume does change, and the FVC changes as well in obstructive disease, but they change proportionally. And since this is a fraction, right? We've got the same proportional change in the numerator as in the denominator. So the value doesn't change because they're both impacted the same way. But when we see this ratio less than 80%, that is when we know that it's restricted disease. Now, depending upon what reference you look at, there can be a little bit of variation in the lower limits of normal. For example, Physio Ex tells us that normally this ratio should be 75 to 85%. Your textbook says something else. We're going to go with a nice, easy number, and it's what I've put in the lecture. We're going to go with 80%. I like to define those variables for you for the purpose of your exams, so that you're not left trying to figure out that ambiguous number. It's more relevant to me and to your future careers that you understand the physiology, that you understand the function of these tests, rather than, I'll just leave it at that. Okay. So this is utilizing you'll see the equipment, but we've got a setup of the human respiratory system. Ooh, I hit a different screen. That was interesting. Sorry about that. I don't even know what I did there. Okay, let's go through the pre-lab quiz. Which of the following statements describing the mechanics of breathing is false? Ventilation refers to the movement of air into and out of the lungs. Well, that's true. Ventilation is measured as the frequency of breathing multiplied by the tidal volume. That's true. Ventilation includes the process of inspiration and expiration. That is true. Ventilation requires exclusively on contracting skeletal muscles. Well, that is not accurate. The diaphragm, for example, is not a skeletal muscle. So there's our correct answer. The contraction of which of the following muscles will increase the thoracic cavity volume during inspiration? So here we need to know which muscles are associated with inspiration versus expiration. And the muscles that increase the thoracic cavity in inspiration are the external intercostals. At the beginning of inspiration, our choices are the diaphragm relaxes, thoracic cavity volume increases, the diaphragm becomes dome-shaped, or the thoracic cavity pressure increases. Look at the timing. The question says at the beginning of inspiration. It is the change in pressure. Sorry, change in volume. I totally had a brain fart there. So our volume increases, which then changes the pressure, but the change in volume happens first. So sorry about that. Okay, at the beginning of expiration, the pressure in the thoracic cavity increases, the abdominal muscles relax, the volume of the thoracic cavity increases, or the external intercostal muscles contract. Well, it's not this last one because the external intercostals are associated with inspiration. So we can eliminate that. Abdominal muscles relaxing doesn't even make sense. We need to know which muscles we're talking about. So we can eliminate that choice. So we're left with pressure in the thoracic cavity increasing, or the volume of the thoracic cavity increasing. So this question is related to the one that we just went over that I incorrectly selected. But that question was asking at the beginning of inspiration. This question is asking at the beginning of expiration. So at the beginning of inspiration, the volume increases in the thoracic cavity. So it's the pressure here. All right, the tidal volume refers to the maximum amount of air that can be forcibly inspired. That's not correct. The amount of air inspired and then expired with each breath under resting conditions. All right, that's a possibility. the maximum amount of air that is forcefully expired. Incorrect. The twice daily changes in breathing that are influenced by the moon. It's this one. The tidal volume refers to the amount of air we move under resting conditions. Okay, so here is the setup. So our equipment is, we've got a pair of artificial lungs that are enclosed in a glass dome. So that controls the volume and the pressure. And then we've got our graph here to measure the changes. So we're looking at time on the x-axis versus the volume moved in liters on the y-axis. So we begin, let me see if I can make this a little bit bigger. We begin, actually, let me just, I'm going to reshare this. I want to make sure that something didn't, that it's showing the video here. Let's do it that way. I just want to make sure that you've got the right video to go along with it. This is actually the third time I've recorded this lecture. Zoom has been having a heyday with it. Okay, so we've got, we're going to hit start as it says. Our air weight radius is set at 5 millimeters of mercury. So let's hit start and we're going to look at the spirogram as it progresses. So we're in our normal tidal breathing here. All right, we're going to record that data. Now we're going to clear our tracings and we will look at, start to manipulate some of these variables. So now we're going to hit start to go into our breathing pattern, but then after 10 seconds, we're going to hit the expiratory reserve volume and then wait another 10 seconds. I'm trying to see if I can make this more visible so I can get all the instructions in, but that's not possible. There we go. That's a little bit better. Okay, so start and then count to 10, time 10 on the spirogram. Okay, and then I hit the FVC at 10 seconds later, which we saw that big inspiration. Let's record our data. All right. And this looks pretty good. It looks similar to the figure that, that is in your textbook. Okay, which muscles contract during quiet expiration? That would be our normal breathing. It is not the external intercostals and diaphragm. That is inspiration. The internal intercostal muscles are involved. We can eliminate choice C here. So we've got our abdominal wall muscles and our internal intercostals. Yep. So it needs to tell us which muscles are involved. So this, please don't ever select abdominal wall muscles because we need to know which ones. We can't just lump them all into one category. Okay, I did that on purpose to show you that point. All right, let's proceed. So now we're looking at the minute ventilation, which is the amount of air that goes in and out in a minute. And we can, this is calculated by taking the tidal volume and multiplying it by the breaths per minute. So we're going to use the values from the second recorded measurement, enter the minute ventilation in the field below. So let's see. Let's see, so we've got to take our tidal volume, which would be 500, and I guess I need to get my calculator out. So that would be 500 times the breath per minute, which is 15. So that is 7,500 mils per minute. Okay, lung diseases are often classified as obstructive or restrictive. Obstructive affects airflow, where restrictive is affecting our volumes and capacities, tying to the loss of elastance and compliance. So pulmonary function tests can help a clinician determine the difference between obstructive and restrictive. Specifically, the FEV1 is the forced volume expired in 1 second. In obstructive diseases such as chronic bronchitis and asthma, airway radius is decreased. Thus, the FEV1 will decrease proportionally, increase proportionally, or not change. Well, the forced expiratory volume is what the FEV1 is. And with obstructive diseases, it's hard to get the air out so that we can get the right pressure and volume dynamics to get the next inspiration in. Okay. All right, let's test this. Now we're going to explore the effect of changing the radius of the airway. So we've been looking at 5 millimeters. Now we're going to take it down to 4.5 millimeters. We're going to hit start. And then after 10 seconds, we're going to do the ERV. And then after another 10 seconds, the FVC, as we did before. But let me clear those original tracings. All right, let's go. There. So there's our tracing. And we'll record our data. So now let's manipulate that variable a little bit more and we'll see the effects. So we're going to decrease the radius by 0.5 millimeter. So we're at 4 now, and we're going to keep doing this until we get down to 3. I'm going to go ahead and leave the tracing on here so that we can compare it. Okay, here we go. All right, so notice that we're not getting as high as we were on our top peak or lower peaks even. We do have some differences. Let's go ahead and we'll do this and then we'll come back and talk about it afterwards. So now I'm going to go down to a radius of 3.5 millimeters and do the same thing. There we go. And there we go. So it's decreasing proportionally again. And now let's go down to 3 and we'll start over. Okay, there we go. So look how the oscillations are much smaller now. We don't have as big of a wave variation. Let's record our data. Let's take a look. So just looking at these 3 values. So we have a radius of 4, 3.5, and 3. And we'll look at the tidal volume significantly decreased as the diameter is reduced. So we're increasing resistance. The ERV is decreasing as well. And look at the total lung capacity. It's decreased as well. Okay, a useful way to express FEV1 is as a percentage of the forced vital capacity. Using the FEV1 and FVC values from the data, calculate the FEV1 by dividing FEV1 by FVC and then multiply by 100. So we're going to look at the radius of 5 millimeters below for this. Oops, I'm sorry. Okay, so we're going to look at the second line here. And it asks us to take the FEV1, which is 3541. And we're going to divide it by the forced vital capacity. So this is the vital capacity here. So it's this number, 4791. And we'll multiply that by 100, and that gets us to 73.9%. So it is reduced. 73.9. So that would indicate that there's restrictive disease since they're changing. Okay, so now we're going to look at that same ratio, but looking at the radius of 3 millimeters. So let's go down here. Okay, so we're taking 436 and dividing it by 621. We're using the vital capacity as the forced vital capacity here. And it gives us a percentage of 70.2. All right, so that is the experiment for activity 1. And we do see that as resistance is applied, we see changes in the amount of air being moved across many of the different volumes and capacities that we're looking at. Okay, let me just pause a minute, and I'm going to get a setup for the next activity, which is going to be exercise 7, activity 2. Just a moment, and I'll be right back, loaded up, ready to go. All right, we're back. In the second activity, we are looking at comparative spirometry, and what we are comparing are different conditions. So we've got normal breathing, we've got moderate exercise, heavy exercise, an asthma attack, and then an asthma attack after the person has used their rescue medication, which is a bronchodilator. So that's what we're comparing. And this will allow us to appreciate some of the differences in these lung volumes and capacities. Okay, so emphysema is associated with the loss of elastance. So the lungs do not go back to their original shape. And then that impacts the alveoli. So here's an example of where the lungs really have to work so much harder, use more muscle in order to breathe. And what happens with a person with emphysema is that their expiration rate is really impacted due to the resistance. Asthma is when the bronchial spasm due to the smooth muscle that is around them, and that does constrict the airway. Additionally, mucus is produced in asthma, so the airway diameter is decreased, but also the viscosity is increased due to the presence of that mucus. So we've got two factors that increase resistance in the airways with asthma. Now, during exercise, our body will change the breathing rate and how deep we breathe to meet the metabolic needs of the exercise. So any of you that are play any sports, you know that after you come off the field, you're usually breathing heavier after a period of strenuous exercise. That is not hyperventilation. That is the normal corrective way that our body responds so that we can get more oxygen in and carbon dioxide out to match the increased metabolism during exercise. So we're using the same setup as we saw in the activity 1. So this is a spirometer, a water spirometer. And then we're going to compare these different conditions. Okay, so the normal resting tidal volume is expected to be what? We've got 600. No, it's way down here. 500. This is the tidal volume, our normal quiet breathing. There we go. 500 is correct. Which respiratory process is impaired the most by emphysema? It's expiration. And that's true of other diseases that, other restrictive diseases, it's expiration. During an asthma attack, bronchial smooth muscle relaxes. Oh, no, it doesn't. Inspiration and expiration are impaired. That's true. Airway resistance decreases. No, that's backwards. It increases. Elastic recoil is impaired. No, this is not, asthma is not a restrictive disease. We're not talking about elastic recoil. So the answer is that inspiration and expiration are impaired. During moderate aerobic exercise, which respiratory variable increases the most? So this would be during moderate aerobic exercise. This would be the tidal volume. Inhaler medications for an asthma patient are designed to rapidly introduce active ingredients. Well, it is true that when you breathe things in, it does get it into the body quicker for most things, but that's not the goal of the rescue medications for asthma. They are designed to counteract the bronchoconstrictions. So they dilate the bronchioles. That's how they work. They do not induce muscle contractions. That would make the problem worse. And they're not associated with inflammation at all. A bronchodilator does not treat any of the inflammatory components of asthma. Now, some of the combination medications that have steroids in them, they do, but the bronchodilator does not. That needs the added steroids if we want to see an effect on inflammation. Okay, so here we are. Here's our spirometer. Oh, look, we've got no person yet, but we're going to look at these different breathing patterns. So we're going to begin with normal. We're going to select unforced breathing, and then we're going to hit start on the spirometer. And what we're going to see appear on the right side of the screen is the spirogram. So here we go. There's tidal volume. And now it's asking us to switch it to forced vital capacity. And here's that change. So this is all tidal volume. And then take a big deep breath in and blow out. Okay. So it wants us to populate the data field. So I'm going to do that. So you can see when I click on it, here's tidal volume. The expiratory reserve volume is at the bottom of tidal volume down to the lowest point. Our inspiratory reserve begins at the highest point of tidal volume and goes up to the highest point. I often see students make mistakes when calculating the expiratory and inspiratory reserve volumes. They do not know where to begin on the other side of the tidal volume. So again, our inspiratory reserve begins at the top of our tidal volume because it is looking at that additional volume, that additional airspace that is created with a deep inspiration. So it doesn't make sense to start it at the bottom because that would have the tidal volume and then a big breath in. Let's go ahead and fill in the rest. So we've got our residual volume, which is the unused space, forced vital capacity, total lung capacity, and then the FEV1. And it calculates the ratio for us or the percentage. And this is at 80%. We're just looking at FEV1 here. Okay, so when obstructive lung disease develops, what happens to the FEV1? It decreases. Okay, so now we're, the way that this activity is set up, we've got a prediction and then we do the experiment, and we do this 3 times through. So this might be a little bit challenging if you're not familiar with these different respiratory conditions. So what it's asking us is, with emphysema, there is significant loss of elastic recoil. And that means more work, more effort is needed to get the breath out. Inspiration is easier because the lung is overly compliant. So calculate the lung volume that is most affected by the emphysema condition. So it's telling us that the inspiration and the expiration are impacted. I'm going to just go ahead and put the, let's see. So this would be, well, it's talking about emphysema, which is restrictive. That affects the expiratory reserve, but it does tie to the inspiratory reserve. It becomes easier to get that breath in. Let's see what that says. Let's take a look so that we can answer that question ourselves. So now we're going to select emphysema. We're going to go back to our normal unforced breathing, and we're going to hit start. Oh, look at the difference in the slope. Wow, the tidal volume looks drastically different than what we saw with the normal breathing. We're going to now switch the parameters for the breathing pattern and finish out our spirogram. So we've got our inspiratory reserve, and then we're blowing out and then going back to tidal volume. I'm now filling in all the data just by clicking on it. And let's take a look. So our tidal volume is the same, but look, that expiratory reserve volume is halved. The inspiratory reserve volume is a third. And then we've got changes in the residual volume, the FVC, as well as the FEV1. So the compared with the normal patient, what happened to the FVC in emphysema? It should decrease. And so, yep, it does. We went from 5,000 to 3,250. So the FVC decreases quite significantly in emphysema. Compared with the normal patient, what happened to the FEV1? Let's go look at our data. So normal is 4,000, emphysema is 1,625. So it's decreased as well. Okay, so now we're going to look at asthma. Our prediction is during an acute asthma attack, resistance is significantly increased by the production of the mucus and then the clamping down, the bronchospasms. So to which lung volume in the spirogram would you see the greatest change in a patient suffering from an acute asthma attack? I do think that these are hard questions for you to be able to answer at this point. But the utility of this experiment through Physio Ex is that we can look at the data and double check our answers after. So let's see. So airway resistance has significantly increased. I'm going to go ahead and say inspiratory reserve volume here. Okay, let's move forward. Okay, so now we're going to change to acute asthma attack, unforced breathing, and we're going to start. Look at how long, how much space is occupied in our tidal volume. Slower. Oops, I selected the wrong one. Now we're going to go to forced vital capacity and hit start. Up. Oh, we're not very low here, are we, compared to what we've seen? Let's get our data. Okay, go back. So our question is, compared with a normal patient, what happened to the FVC? So 5,000 for normal, 3,750 for the acute asthma attack. So it decreased. Compared with the normal patient, what happened to the FEV1? So now we're at 4,000 versus 1,500. It decreased as well. So both the FEV1 and FVC decrease in obstructive disease, usually very proportionally. So that means we get a normal ratio when we divide them out. Okay, now we're going to look at the episode of an acute asthma attack, but what happens when the inhaler is used to try to rescue that? So we've got our, which lung volume remained relatively unchanged when comparing a patient with acute asthma versus with the inhaler versus normal. So what we're hoping to see with the use of the asthma inhaler is that the values get close to normal. So we could look at the differences between normal versus acute asthma as a way to predict the answer to this question. So we do have a reduction in tidal volume in the ERV, just a little one in the inspiratory reserve, 3,000 to 2,700. Our residual volume is actually bigger in asthma. Our forced vital capacity is slightly decreased in asthma, and so is the FEV1. This is a little tricky, so we're going to go with the inspiratory reserve went from 3,000 to 2,700. But then our tidal volume is very different too. Let's put tidal volume. I'm just curious to see what it tells me at the end. Okay, so now let's check it out. We're going to go with asthma attack plus the inhaler, and we're going to look at our normal unforced breathing first. Here we go. So he took a puff of the inhaler and then blew. Here we go again, another puff of the inhaler, and we're getting a more extreme difference. So which value in the spirogram never changed from that of the normal? It is the total lung capacity. It's always 6,000, no matter what condition we're looking at. Okay, during moderate aerobic exercise, the human body will change its respiratory cycle in order to meet the increased metabolism. During heavy exercise, there are more changes in respiration that are needed to meet the demand. So which lung volume will change more during moderate exercise? Is it the expiratory or the inspiratory reserve? It's the inspiratory reserve. Okay, now let's go to moderate exercise, and we're going to hit start. Here we go. We're not going to change the breathing pattern here. Okay, let's get our data. Got it. Okay, and now we're going to go to heavy exercise, our last condition, and let's see. Whoa, look at the difference. So the oscillations are much bigger, but look at the rate. Look how much faster the person is breathing. That is significant difference there. So for both types of exercise, the tidal volume as well as the rate were increased. Compared with normal values, did the tidal volume or breathing rate increase more during moderate exercise? So let's look at moderate exercise. Tidal volume is 1875 compared to 500. That is a huge change. What about breathing rate? In order to, well, we can just look at here, we can look at this part, look at our spirogram. The rate has increased, but we would actually need to work out the math to get that number. It is the tidal volume that changes more. It's part of the benefit of exercising is to increase your tidal volume. And that does it by digging into that residual volume that isn't used. All right, that's it for the exercise. Exercise 7, activity 2. I am going to pause us for a moment and come back in just a second with activity 3 all loaded up for you. All right, here we are with activity 3 of exercise 7. So we're looking at the effect of surfactant and interpleural pressure on respiration. So we've got two variables that are manipulated here, the quantity or presence of surfactant, and then the what that interpleural pressure is. So keep in mind that the interpleural pressure is the pressure that is in that cavity, the pleural cavity, which is created by the barrier, the epithelial layer of the lung, and then the pleural membrane itself. So inside is the space where the interpleural pressure is. This is the area that is filled with surfactant to allow the pleural lining to easily slide by the surface of the lung, avoiding friction. If friction is created, that could lead to inflammation, which would not be a good thing. All right, so what we can appreciate from this study or this experiment is that process or what happens in a pneumothorax. And a pneumothorax is created when the pleural lining is ruptured. And what that does is it essentially makes the pleural space equal in pressure to atmospheric pressure, which then can collapse that lung. So atelectasis is lung collapse. And oftentimes, even in people that have asthma, they will have atelectasis at the base of their lungs, just because they're not able to fully use their lung volume. And then the parts of it that aren't expanded, well, they rub against each other. And essentially that becomes more residual volume in the lung. So we're going to look at a similar spirometry to what we've seen, but this time we have a valve that allows us to manipulate the interpleural pressure. Plus we can introduce surfactant in this activity. Okay, so here is our pre-lab quiz. Which of the following statements about surface tension is false? Molecules of a liquid are attracted more strongly to each other. That's true. Surface tension resists any force that tends to increase surface area. Let me think about that in a minute. That's true. Surface tension acts to increase the size of the alveoli. Surface tension occurs at any gas-liquid boundary. That is true. So it is choice C that is false. Surface tension would not have anything to do with the increase in the size of the alveoli. Okay, which of the following statements about surfactant is false? So surfactant is a detergent-like mixture of lipids and peptides to decrease surface tension. That is correct. Surfactant is part of the aqueous film covering the alveolar surfaces. Yeah, that's correct too. Surfactant reduces the amount of work required. Well, that's the whole point of it. That's true. Surfactant works by increasing the attraction of water molecules to each other. That is not what surfactant does. Surfactant is made of lipids, first of all. So it wouldn't mix with water. Okay, just before inspiration begins, the pressure within the interpleural cavity is referred to as the interpleural pressure. No, is lessen the pressure within the alveoli. Okay, possibly. Is influenced by the tendency of the chest wall to collapse. Well, that would mean we all have collapse. Yeah, it's choice B here. It's less than the pressure in the alveoli, and that helps to establish that bulk flow gradient. The respiratory condition of pneumothorax refers to the pressure in the interpleural space becoming lower than atmospheric, the removal of air, any opening that equalizes interpleural pressure with atmospheric pressure, or a bacterial infection. It's choice C here. Because when there's a pneumothorax, that pleural lining has been ruptured. And that is involved in those gas exchange surfaces. Yep, that's right. And then a pneumothorax is able to lead to lung expansion. No, that's the opposite. Atelectasis, that it does. Interpleural pressures that are more negative, or the need for Lorax. So it is choice B. All right, let's move to the experiment. Okay, so here we've got a similar setup to what we've been looking at. Well, this is more similar to what we saw in activity 1, but this time we have the ability to manipulate a valve in the lung here. Plus we can add surfactant. So let's begin. So check out the waveform here. This is our tidal volume, just to give us a baseline. We're at a breathing rate of 15 breaths per minute, which is in the normal range. Record our data. Okay. So now we're going to add surfactant, and we're going to look at the comparative tracings on the spirogram to see if there is an increase in the tidal volume or another volume once surfactant is added. So we're going to do 2 pumps of it. And now we will hit start. Oh, yep, already we can see the difference. Notice that the blue line, the blue dotted line, is higher. Its maximum height is more when surfactant is added. We're not seeing a decrease on the lower end of the tidal volume, just on the top end, if you will. Okay, what effect will adding more surfactant have on the lungs? Airflow decreases. No, that makes no sense at all, because the purpose of surfactant is to help increase airflow. Airflow will further increase, or it stays the same. Well, I imagine there's a certain point where it may stay the same, but the question is that biologically relevant? We do know the purpose of surfactant in that it makes it so that those surfaces are able to have maximum gas exchange. So I would say that it increases airflow. Okay, so now we're going to hit surfactant twice. Hit start. Look, so now our line is getting even higher. Notice again, our lower end of the tidal volume is exactly the same, but we are increasing the overall waveform by adding more surfactant to the lungs. Let's record our data. Got it. Let's take a look. Okay, so our breathing rate is the same, and then we've gone up in surfactant. And look at the total flow. Let's just come right on over to the total flow. So with 0 surfactant, it's just under 100 mils per minute. But when we add in 2 pumps of surfactant, it's about 140 mils per minute. When we add in 4, it's about 179 mils per minute. So it is increasing. All right, let's clear off and flush out the system. Okay. Why did the sequential additions of surfactant change this lung system? Well, that's another way of saying, what effect does surfactant have on the surface tension? So we've got, let's see our options. We've got surface tension was decreased. Okay, that makes sense. The addition of more fluid to the lungs improves airflow. Oh gosh, that is so incorrect. I mean, think about what pneumonia is. Pneumonia is the presence of fluid in the lungs. Look at the situation that's happening with the pandemic right now. Having fluid in the lungs is a very bad thing. It is a pathological condition that impacts airflow. So B is wrong. Surface tension is increased. Well, that would not help us. The addition of more fluid to the lungs increased the pressure. So here's our answer. Okay. Premature infants often have difficulty breathing because the amount of surfactant in their lungs is too low. This is why mothers that are suspected or known to be delivering prematurely are given medication or even a shot of steroids because it induces the production of surfactant in the infant. But premature babies here in the United States are all treated by receiving surfactant. And what a difference it made. I don't know the statistics to tell you how many premature baby deaths were avoided by adding in surfactant, but it's significant. Okay, let's go. So now we're going to look at our normal tracing to begin with. So just normal tidal volume. Notice that both lungs are expanding and are contracting at the same rate. And we have a nice waveform here. Let's record our data. And now what we're going to do is we are going to open this valve and look what it does. So now the intrapleural pressure is equal to atmospheric pressure, and it has collapsed that lung. Oh, big difference here. Look at how much lower everything is. Even the difference between the maximum and the minimum of the waves has decreased with the collapsed lung. We're way below here. Okay, so what happened to the left side of the bell jar when the valve was opened? Well, interpleural pressure became more negative. It can't become more negative if the system is opened. Interpleural pressure equalized with atmospheric pressure. That does make sense. The lung on the right side of the glass jar became larger or airflow increased. Here we go. What will happen to the collapsed lung in the left side of the glass bell jar if the valve is closed? So if we close the valve, which simulates fixing the hole in the pleural cavity, what should happen? Will the lung reinflate in one breath? Oh, I doubt it. Will the lung reinflate over several breaths? Will the lung remain collapsed, or will it collapse even further? This is tricky. Let's actually look at the data. So fixing the problem should allow for the pressure to correct in that interpleural pressure to correct, which should get us back to normal breathing. But the question is, does it happen over one breath or does it happen over several breaths? So let's take a look. I'm going to put over several breaths. Okay. So let's click the valve, and now we're going to close it. So the valve is closed. We are going to hit start. Ooh, look where we are. Just like I thought. Yeah, we're still below. We're still way lower than we were. We're essentially having the same tracing as when the lung was still collapsed, because guess what? It's still collapsed. Did the collapsed lung reinflate? No. That's why it stayed at the same waveform. Let's reset our values and hit start. And this way we can now look, both lungs are the same. We fixed the lung problem. And the tracing's going right back over the original normal value. So we have fixed the problem. Okay, so our breathing rate's the same, the surfactant's the same, but look, now our pressure has allowed, we've gotten our lower pressure back, and that allows for proper flow, and we get back to our total flow that is about 100 mils per minute. Let's scroll up to the top. So this was our beginning value, close to 100 mils per minute. So that's it. We fixed the problem by plugging up the airspace and allowing time for things to equalize. I can share with you from experiencing asthma with atelectasis that it does take time. First of all, asthma is an inflammatory component, and inflammation is never something that just comes instantly or disappears instantly. There's a whole cascade of events associated with it. Well, hopefully that was helpful, and I'll see you back soon. So this is lab exercise 12. I mistakenly listed it as being lab exercise 13 in one of the headers for the in Canvas, but the lab itself is lab 12. Take care, everybody. I'll see you back soon. Bye-bye.